Your current understanding holds that Andromeda sits 2.5 million light-years from Earth. The nearest star, in your view, resides 4 light-years away. You're convinced that spatial separation can be quantified with precision and certainty. Yet consider this. Perhaps every distance measurement you've ever conducted is fundamentally flawed. What if separation itself isn't an inherent characteristic of existence, but merely a perception constructed by your consciousness? What if, at physics' most basic level, space contains no measurable gaps whatsoever? The revelation I'm about to share will reshape your entire conception of spatial reality. Separation feels like the most self-evident phenomenon imaginable. You're positioned at some remove from your viewing device. Our moon orbits at roughly a 250,000-mile radius. Our sun maintains approximately 93 million miles of distance. These measurements appear genuine, unchangeable, immutable. Separation simply represents how far objects exist from one another. It seems like the most straightforward notion within physical science. Yet simplicity frequently conceals the most profound enigmas. And separation, appearing so obvious, emerges as among the most fundamentally misunderstood principles in all of science. What separation signifies is radically different from your assumptions. It isn't fundamental. It isn't unchanging. It isn't genuinely authentic in the way your intuition suggests. Comprehending why demands a journey through quantum physics, Einstein's relativity, holographic theory, and the essential nature of space itself. Begin with something seemingly obvious: light's velocity and its implications for measuring separation. When astronomers declare Andromeda resides 2.5 million light-years from us, they're articulating something resembling a separation measurement. Yet it's fundamentally a temporal measurement. A light-year quantifies the span light traverses annually. Declaring something sits 2.5 million light-years away indicates light requires 2.5 million years for transit from there to here. But here's the complication. You're not determining Andromeda's current position. You're calculating where Andromeda existed 2.5 million years ago, when that light commenced its journey. By the moment photons reach your telescope, Andromeda has relocated. It has been repositioning itself across 2.5 million years. Your measurement indicates the separation to a phantom, where Andromeda resided millennia past, not its present whereabouts. Additionally, due to universal expansion, Andromeda's genuine present-day separation differs from the path light traversed. Spacetime grew during the 2.5 million years light was in transit. Consequently, light's trajectory differs from the current gap separating you from Andromeda. Every large-scale separation measurement combines no fewer than 3 distinct separation ideas. The pathway light followed, the separation when radiation left its origin, and the contemporary distance accounting for universal growth. These represent entirely different measurements. Which one represents authentic separation? The resolution is that none holds greater authenticity than others. Each provides legitimate descriptions of separation, depending on which inquiry you're investigating and which perspective you're employing. No singular factual answer exists regarding how remote a far-off galaxy truly is. Currently, at cosmic dimensions, separation remains observer-influenced and definition-influenced. It lacks absolute objectivity regarding physical reality. Yet this represents merely the start. Einstein's special relativity advances this demolition of separation's unchangeability substantially further. In 1905, Einstein established that separation transforms relationally. Not somewhat, not partially, but absolutely, fundamentally, and arithmetically contingent upon your velocity. This is the fundamental principle. A measuring rod traversing you at extreme velocity becomes abbreviated compared to an identical measuring rod remaining stationary. Not because the rod undergoes literal compression, not because forces press against it, but because space-time structure causes moving items to occupy reduced spatial dimension along their movement trajectory compared to stationary items. Physicists term this phenomenon length contraction, and rigorous investigation has validated it experimentally. At 1/10 light speed, items compress roughly 0.5% along the movement direction. Minimal, yet observable. At 90% light speed, compression yields roughly 44% of the resting dimension. At 99% light speed, compression results in roughly 14% of the resting dimension. As you approach light speed, length approaches nothingness. What implications does this carry for cosmological measurements? Separation hinges on reference systems. Aboard a spacecraft moving at 99% light speed toward Andromeda, the gap separating you from that galaxy isn't 2.5 million light years. It amounts to 2.5 million light years divided by the Lorentz coefficient, which at 99% light speed produces a measurement of approximately 350,000 light years. A person stationary on Earth, and you would establish entirely distinct measurements for the identical galaxy. Both calculations prove legitimate within their respective frameworks. Absolute separation lacks existence. At light's velocity, the compressed measurement becomes nil. From illumination's standpoint, were it capable of perspective, which we've shown previously it doesn't possess, the span from source to endpoint would equal 0. Every cosmic measurement registers as 0 when considered from light's viewpoint. The whole detectable universe has 0 extent from illumination's frame of reference. Separation in space already lacks absoluteness. It fluctuates based on your velocity. It depends on your frame of observation. Various observers compute differing measurements between identical locations, and each possesses equal legitimacy. No intrinsic actuality exists regarding authentic separation, independent of the measurer's identity and movement characteristics. Yet this fails to represent distance's deepest breakdown point. Einstein's general relativity extends further. Under general relativity, space undergoes bending. Mass and power deform space-time structure. Adjacent to dense material, space bends substantially. This signifies that separation between locations doesn't stem from unchangeable underlying geometry. The arrangement of matter and power between and surrounding those points establishes it. In black hole proximity, space contorts so radically that the measurement from beyond the boundary toward the central point grows essentially boundless. Albeit a black hole demonstrates measurable extent from external observation, an approaching witness perceives black hole internals as possessing tremendous volume, substantially exceeding external appearance. Black hole interiors harbor immense spatial volume beyond external accessibility. This unveils that separation isn't an unchanging quality. Matter and power distributions establish it. Modify matter and power patterns, and every measurement throughout existence transforms. Separation isn't the foundation supporting physical phenomena. It functions as a physical characteristic itself, transforming with physical conditions. Warped geometry additionally indicates that the briefest route joining two locations isn't a straight connection. In twisted spacetime, briefest paths, termed geodesics, adhere to space's bending. Measurement along a geodesic hinges on bending, with bending determined by mass and power arrangement. Positions appearing neighboring in level space might be distant following the geodesic route if tremendous mass sits between them, or might appear contiguous due to light bending around the dense thing. Even the straightforward idea of locations residing at equivalent positions becomes perplexing within black holes due to extreme curvature. Positions at matching spatial locations per one labeling scheme can occupy vastly differing positions per alternate labeling. The terminology we employ for noting points in spacetime proves arbitrary. Alternate terminology selections yield entirely distinct descriptions of points' proximity and remoteness. This transcends mathematical convention. Actual phenomena respond to terminology selection. A powerful gravitational influence in one terminology appears as undisturbed empty expanse in another. A tremendous measurement in one terminology appears as negligible in another. Factual, terminology autonomous explanations regarding spacetime concern its curvature and configuration, not straightforward separations. Now arrives the most extraordinary and astonishing method through which spatial separation becomes merely appearance. Quantum coordination and hologram-based principles. Quantum coordination ranks among nature's strangest occurrences. When particles engage and become coordinated, they comprise a singular quantum phenomenon, characterized by singular mathematical expression, irrespective of subsequent separation extent. Determine a characteristic of a single particle, and you instantaneously recognize the analogous characteristic of its partner, independent of intervening space. Einstein labeled this phantom-like activity across distance and exhausted considerable effort attempting to demonstrate its impossibility. His presumption proved incorrect. We've substantiated coordination in innumerable investigations. Two coordinated particles might occupy opposite borders of the detectable realm, and they continue comprising one quantum phenomenon. Physical separation doesn't dissolve coordination. Measurement disparity doesn't reduce it. Two particles, coordinated yet billions of light years asunder, maintain tighter quantum association than uncoordinated particles making contact. This communicates something exceptional. Quantum mechanical association and spatial association constitute wholly distinct notions. Particles can be physically remote, yet quantum mechanically attached. Particles can occupy adjacent areas, yet quantum mechanically distinct. Spatial measurement doesn't represent what genuinely transpires at quantum reality's level. Physicist Juan Maldacena engineered among the greatest breakthroughs in theoretical physics history during 1997. He uncovered an exact mathematical relationship termed anti-de Sitter conformal field theory linkage between gravitation theory within selected warped space-time and quantum mechanics theory without gravity inhabiting that space-time's boundary. The gravitation theory occupies a space possessing one additional dimension beyond the boundary quantum mechanics theory. Yet both depictions demonstrate perfect equivalence. All measurable features in one framework translate flawlessly into the alternate framework. Both depict identical physical phenomena from wholly contrasting angles. This represents the hologram principle in its most accurate mathematical interpretation. Our three-dimensional spatial experience can be exhaustively and precisely portrayed through a framework living on that space's two-dimensional boundary. The third-dimensional element, creating depth sensation and distance perception, isn't essential. It's manufactured. It originates from the boundary framework's quantum coordination pattern. Contemplate this concept's implications regarding separation. Within the three-dimensional inner framework, measurements emerge. Material relationships seem near or far. Gravitational impacts hinge on measurement. Space-time structure governs measurements. All seems principal and tangible. Yet, in the two-dimensional boundary framework, no inner measurement exists. The two-dimensional boundary framework contains its own measurements, its two-dimensional curvature. Yet the three-dimensional depth, the measurement inward, doesn't signify measurement within the boundary framework's geometry. It corresponds to something wholly distinct. Distinctly, it mirrors the frequency bandwidth of the boundary framework. Elevated frequency actions in the boundary framework correspond to minute measurements from the boundary inward. Depressed frequency actions correspond to expansive measurements from the boundary. What we perceive as measurement in the third spatial dimension actually represents frequency bandwidth. Within the underlying quantum framework, measurement isn't essential. It constitutes a technique for explaining quantum mechanical correlations among components at differing frequency bandwidths. Spatial depth signifies an arising characteristic originating from the boundary framework's quantum coordination composition. This constitutes not mere approximation or representation. This constitutes exact arithmetic equivalence confirmed with extraordinary accuracy. Specifically, the straight-line measurement within the hologram illustration truly originates through quantum coordination. Contemporary investigation by scholars, including Mark van Ramsdonk, Brian Swingle, plus further researchers, has rendered this linkage noticeably more obvious. They've shown that space-time's composition, encompassing its complete measurements plus deformations, derives from the quantum field's coordination composition. Distinctly, a measurement called coordination power, measuring quantum correlation among regions within a quantum arrangement, establishes the space-time's composition. Space-time regions appearing neighboring reflect powerfully coordinated regions within the quantum rendering. Space-time regions appearing distant reflect minimally coordinated regions. Spatial measurement corresponds to quantum coordination. Both portray equivalent fundamental characteristics. Van Ramsdonk presented this utilizing an elegant scenario. Examine the boundary framework's quantum condition and minimize coordination separating its halves. Which occurs within inner spacetime? Inner spacetime fragments into separate components as coordination diminishes. Keep reducing coordination toward nil, and inner spacetime's fractions grow entirely unconnected, with unbounded measurement among them. Restore coordination, and the fractions reconnect, and measurement contracts. This discloses something profound: space-time interconnection. The reality that different spatial regions stay linked with restricted measurements originates directly from quantum coordination. Remove coordination and existence collapses. Introduce coordination and existence becomes stitched together. Measurement isn't something space inherently possesses. Measurement constitutes a manifestation of quantum coordination among the elements creating reality. This realization produced one of the most electrifying contemporary breakthroughs in theoretical physics. The ER-EPR suggestion, offered by Maldacena plus Leonard Susskind person, Einstein-Rosen structures, wormholes joining distant space-time sections, are abbreviated as ER, following Einstein and Rosen, who initially explained them mathematically. Einstein-Podolsky-Rosen groupings, maximally coordinated quantum particles, are abbreviated EPR, following the renowned 1935 investigation by Einstein, Podolsky, plus Rosen. The suggestion states ER translates to EPR, meaning an Einstein-Rosen structure separating black holes equates to EPR coordination separating those black holes. A wormhole joining distant space regions matches supreme quantum coordination separating those regions. The geometric connection via a wormhole, plus the quantum mechanical connection via coordination, represent equivalent phenomena expressed via differing descriptive methods. Its implication? Coordinated particles stay connected via a form of quantum wormhole, a geometric tunnel through space-time manufactured by their coordination. Particles appearing physically separated because you cannot perceive the quantum tunnel joining them actually get geometrically linked via that tunnel. Their separation constitutes false impression, stemming from examining the inappropriate depiction level. Our typical concept of measurement, the measurement you establish utilizing instruments or light detection equipment, constitutes the enlarged emerging depiction. Fundamentally, the authentic framework is coordination. Coordinated particles don't maintain remoteness from one another in any basic form. They connect. Measurement represents a macro-scale deception, surfacing while disregarding quantum intricacies. Looped quantum gravity supplies a further viewpoint regarding why measurement isn't essential. Within looped quantum gravity, space-time lacks smoothness plus steadiness at minuscule magnitudes. Rather, it comprises discrete quantum sections, infinitesimal bits of reality termed spin lattices. Spin lattice nodes represent volumetric quantum. Connections separating nodes represent sectional quantum. Measurements in looped quantum gravity don't constitute perpetual values. They're distinct, quantified, coming within tiniest segments matching the Planck dimension, roughly 10 to the negative 35th power of a meter. At dimensions beneath the Planck dimension, measurement's meaning turns into nothingness, not merely unmeasurable, nothing.